like to talk to you about a very exciting recent project, which is Asymptotics. And what this is, it's a new kind of approximation. I say new because in mathematics, geometry is ancient, algebra is old, calculus is recent, and asymptotics is only 100 years old, so it's recent for us. So it's an approximation technique, and it's still under development, so it's kind of like an art. It's not quite a science. So what I'd like to do today is to talk about this wonderful way of doing approximations. And so here is the plan for my talk. So I'm going to begin by telling you exactly what is asymptotics and what you can expect when you do asymptotics in the Wolfram language. Now, this subject has got a long history which led to the current state. So I'll talk a little bit about the history of asymptotics to motivate why we do things the way that we do. And once that introduction is over, then I'll give examples of differential equations and integrals which can be computed asymptotically, approximately, using the new technology. Asymptotics for discrete things like differential equations and sums, and then algebraic equations, which is the most recent addition. So together, you get a pretty complete picture of what asymptotics in the Wolfram language looks like. So let's begin with the question, what is asymptotics? Well, I think of asymptotics as being a very powerful alternative to exact methods and numerical methods. So at the moment, we have exact methods for, let's say, integrals. We've got integrate, which does that. And that's, of course, very popular. That's why people use Mathematica and the Wolfram language. But some people may also like to use numerical methods because they are very robust and quite powerful. But there are cases where both these methods fail. So fluid dynamics is a good example. So for a long time, people had tried to understand how does a viscous fluid move? And the answer to that was given by Navier and Stokes in the 18th century. And they said, in the 19th century, and they said that, there's a wonderful set of equations called Navier-Stokes equations, which can help you do that. Unfortunately, those equations cannot be solved either exactly or numerically without some tricks. And the real trick for doing so was discovered by the German engineer Ludwig Prandtl in 1904. So what Prandtl said is that you can imagine that around such a viscous fluid, you actually have this kind of thin boundary layer in which everything takes place. So you have a wing over here, you've got a thin layer around it, and then the fluid flows around that boundary layer. And then what you can do is, by focusing on just that small, tiny region around the wing, you can forget what's happening elsewhere. It's almost kind of ideal motion. And that way, Ludwig Prandtl actually launched the field of aerodynamics. And of course, we know aerodynamics is very useful. So that's where asymptotics began. It began with the work of Ludwig Prandtl in terms of real applications. So the question is, what can you expect when you do asymptotics in the Wolfram language? Well, in practice, what asymptotics give you is a useful approximate formula for solving a problem. So you might get a formula, and that formula is quite nice, but typically that formula is part of an infinite series. So potentially you get lots of better approximations simply by taking more and more terms of that infinite series. And here's where the problem is, because these series are often divergent, and hence to find out exactly how many terms you require is an art. If you take too few terms, you get a poor approximation. If you take too many terms, you might get a completely wrong answer. And therefore, we talk about the art of asymptotic approximation. Okay, so now let's talk a little bit about the history of this wonderful subject. So asymptotics began with, like all good things, began with Isaac Newton and Leibniz, who explored calculus using infinite series. To them, they only knew infinite series. There was no sine, no cosine, no other functions. They were explorers. In the spirit of good explorers, they didn't worry about things. They just went on and on. And it was only in the 18th century that Euler realized that in fact we do need to worry about these divergent series. But they were so fond of all the approximations from asymptotics that they decided to approach this whole problem pragmatically, and they said, let's not worry about it, we can just go on and on. But of course people started getting worried, and in the 19th century Cauchy and Euler said, okay, this is too much, let's now try and understand convergence in a very rigorous fashion. But as you all know, the rigorous kind of approach is not very useful, and the electrical engineers complain that's really bad. You can't stop over here. We need to go back to pragmatic uses. So we had the pragmatists from 18th century and the rigorous from 9th century battling it out, and finally it was Henri Poincaré who said, oh, let's combine the two approaches and talk about asymptotic expansions. So asymptotic expansions kind of combine both the convergent and the divergent series into one wonderful subject. Okay, so with that background of the history, let's now talk about some examples of asymptotics. So here you have a second order differential equation. In fact, you recognize that this is a differential equation for cosine because the second derivative is the negative of the function. The value at 0 is 1, the derivative 0 is 0. And if you use the function asymptotic solve value, then you get back the first 8 terms in this case over here. And as you take more and more terms, you get better and better approximations. So the solution kind of winds itself on the exact solution slowly as the number of terms increases. That's of course a very nice, ideal situation. Nothing to do over there. It works wonderfully. So that's the Taylor case, if you like. Now, to go a step further, let's look at something where you actually have problems. So that's the notion of a regular singular point. So here's the Bessel equation. It's got order 1/2. And you see over here that you have an x squared term. And that means when x is 0, you have a real problem because this term will disappear. And in such a case, what you get back is a so-called Frobenius series. It's got square roots in it and all kinds of fractional powers, much harder. But even in this case, you can actually plot both the regular and the singular solutions. So this solution over here is regular, no problems. That solution is singular. It's problematic at 0. You can see over here dividing by 0, but together they give you a complete picture of this Bessel equation. Okay, so now let's go on to something even harder where you have a thing going really wrong, and that's the notion of an irregular singular point. So here's the Airy equation, and if you transform it so that you work at infinity for very large x's, things start going really quite wrong. And the reason why they do is because you actually need a different scale to operate. You need a kind of exponential scale to operate like over here. And you see over here that you have the original functions, the blue over here and that one over there, and the asymptotic expansions are no good at an early stage, but then eventually they become wonderfully accurate for this rather difficult problem. So you have these singular points, but they can be tackled quite well by simply using a different asymptotic scale. Okay, so now here's a nonlinear equation. Now typically when you have a nonlinear equation, it's rather difficult to find a solution, an exact solution for it. Let me try and see if I can get a series expansion for it. So I try to get the first 37 terms over here, and I just got back 3. So what is happening? Well, what is happening is that this solution over here is actually an exact solution. And so what you see is that you actually have an exact solution coming from an asymptotic method. That's quite remarkable. You just can't imagine getting such a nice solution from such a general method, but it does happen over here. So this was one of the great things for me to see that you can actually get exact solutions from these asymptotic methods. Okay, so now let's go on to the problem that Prandtl studied. Namely, he said you have a fluid over here and you have this wing over there, and you want to study the motion of a viscous fluid, that fluid around it, and your boundary layer. So in the 1940s, people like you have a lot of mathematicians tried to work out these so-called singular perturbation problems, which try and mimic the fluid dynamic case in a very simple manner. So you have a perturbation problem, that's the perturbation parameter, and when the perturbation parameter gets very, very small, things start to look very, very different. So if I give the problem to astronaut D-solve value and I say, give me a first order perturbation expansion, I get back this simple answer. Now, the exact solution in this case is much, much more complicated. But you see over here, I've actually had to fudge things a little bit to show that they are different. So the exact solution and the approximate solution are almost the same, although the first one is very, very simple and the second one is very, very complicated. So my point is that very often you can get excellent results from asymptotics without much of a difficulty at all. So this notion of perturbation problems is what gets used all the time in applied mathematics, and these boundary layer problems have been studied extensively by both applied mathematicians and people who actually do engineering and other things. Okay, so now let's go on to integrals. So here is a rather difficult integral. It is absolutely impossible, at least from my point of view, to find an exact solution for this problem of integrating the function. You see, it's got a sharp peak over here at 1, and then it's almost 0 elsewhere. But even for this rather difficult problem, the asymptotic integrate function can return to you a nice, simple approximation in terms of the parameter omega over there. And if you take a large value for omega, you get an answer which compares quite well with the numerical answer. So that's the approximate answer, that's the numerical answer, and now you can get an even better approximation by simply asking for one term more over here, and you get back that over there. And that answer, in fact, matches almost perfectly with the numerical answer. So that's a remarkable thing about asymptotics. It works really well when it does. You shouldn't need to worry about anything. It just takes over and does its job. But the Laplace method was, of course, discovered by Pierre-Simon Laplace in the context of probability theory. And since then, these methods have become quite useful in all kinds of applications. Okay, so that's the kind of exponential case where you've got a sharp exponential peak over here. But beyond this, people like Kelvin and Stokes said, okay, can we do the oscillatory case? So here's an oscillatory function. You see the exponential over here has got an I on top. So it's very wild exponential behavior. That's the exponential function. Again, no hope of getting a really good answer over here. And luckily, you can still get a very good asymptotic approximation in this case. And you can compare the numerical approximation and you do get back quite a reasonable answer. So this function asymptotic integrate is quite powerful. It can take fairly difficult input and still give you a very simple output. Right, so I do see a question about what's the difference between an asymptotic solution and a Chebyshev solution. Well, they are just different in technology. These Chebyshev solutions could be thought of as being kind of asymptotic, but the asymptotic regime is much, much bigger because you can allow exponential functions, you can allow fractions, so it's a much, much vaster area. Okay, so we spoke about this so-called method of stationary phase, which actually does what it does is basically tries to get the approximation over here by looking at the peak over there. Okay, now the question is, what happens if things go divergent? Well, so here's an example where you have a pretty simple function to integrate from 0 to infinity, and I ask for the first 8 terms of the approximation in terms of this parameter x. And what you see over here is that this series is wildly divergent. And in fact, there is no hope of getting this series to converge for any non-zero value of x. Because basically, if you fix x, then these coefficients will quickly overpower and go off to infinity. But the nice thing is that even this very simple approximation over here gives you back a wonderfully accurate answer. So you might tell yourself, oh, well, if I took 150 terms, let's say, things might get better. Well, let's do that. And lo and behold, you get a completely wrong answer. So with asymptotics, and you have divergent series, and when you have divergence, you need to be very careful. You must take the right number of terms. Therefore, asymptotics is an art, not a science. Okay, so we spoke about asymptotics of integrals, and for the last year or so, whenever I see an integral, I try asymptotics on it. So you may all have read Richard Feynman's biography. Surely you're joking, Mr. Feynman. And in that biography refers to a book by Woods from which he learned advanced calculus. And he said that, I use differentiation under the integral sign to do these questions. So here's the example from the book by Woods, which Feynman used to study integration or differentiation for integration purposes. And I tried to ask for an integrate, and within just a fraction of a second, I got back an answer. Now, although I requested 8 terms, I actually got back only 1 term. That was surprising. Okay, and I said, what's happening over here? Well, if we do a series expansion, what you see is that you have the first term over here, and then everything else over there, but the everything else over there has got an integral equal to 0 over the required interval. So the answer is just 2 pi log a, however many terms you take. So in fact, this rather difficult integral has been found exactly by asymptotic methods, and you can check that if you wait for around 30 seconds, you do get back the same answer from integrate. So asymptotics, when it works wonderfully, but you have no guarantee that the answer is correct. Okay, so here's my next example, which talks about difference equations. So I spoke about differential equations, I spoke about integrals, and now let's go on to difference equations. So here's a sequence, and we would all agree that this sequence is wildly divergent. In fact, this sequence is a sequence of involutions. So what's an involution? It's a permutation which can be written only using disjoint transpositions. So that's a nice sequence. The question is, can we find an approximation for it? Well, I told myself, let's look at the sequence and give it to this find sequence function. So it doesn't know the answer, but it does know the difference equation satisfied by the sequence. So difference equation is that every term is related to the previous 2 terms by some relation, and those are the first 2 terms. The 1 over here and the 2 over there are the first 2 terms. So what I told myself is, okay, can I now use something else to solve a problem? Well, I made this number inexact, and then I gave it to this new function, and I get back to the approximation. Doesn't look very promising, but when I try it, I get back an answer which compares really very nicely with the actual answer. So, but my point over here is that given this wildly divergent sequence, you can still get a wonderfully simple approximation for it, which gives you just the right answer for very large values of the number n. Okay, so on to the next feature. So that's asymptotic sum, and I'm going to talk about a harmonic sum. So what harmonic over here means is you can think of this as being like a Fourier series, and what we do internally is we compute a Mellin transform, look at singularities, come back, do some more analysis, and give back the approximation, which is wonderfully nice for small values of x. So the asymptotics over here is pretty heavy on technology. It uses Mellin transforms, it uses series expansions, all kinds of stuff. So I'm now on to my last example, but to me this is the most beautiful example. That's the curve. It's got 3 loops in it. Now if you think about it, this point over here is a singularity. Because if you get here, you don't know where to go. You could go here, 1, 2, 3, 4, 5, 6. 6 directions. Question is, how do we approximate those 6 branches of the curve? Well, the answer was given, believe it or not, by Isaac Newton in his work, and he said that in such a case you will have 4 branches of asymptotics on the right, like you see over here, from asymptotic solve. You'll have 2 from the left. So you got 4 here, 1, 2, 3, 4, 5, 6 answers. Put them all together and you get this wonderful picture of the curve with all its different branches. So that's been a whirlwind tour of asymptotics, differential equations, integrals, differential equations, sums, arbitrary equations, and all that together will, I hope, make you agree that asymptotics is a very powerful third mode of computation in the Wolfram language.